right. So, yeah, thanks for the opportunity, Grant. So, what I was thinking of, adapting a few slides to give more on the technical side, what the opportunities are with microgrids, demand response, and energy efficiency, especially for smaller cities, and showing the example of Envision Charlotte, being quite active right now. So let me see what does. Oh, there it goes. Okay, so I've got a few slides just on the energy security and independence, and I think you referenced some of the bills and initiatives from Department of Energy on this issue. So that's probably a duplication a little bit. Trends and delivery of end use. There are some interesting trends, and I think you mentioned a lot of them already. I want to spend a little bit of time, especially about the issues which they found in California and other where we have high penetration levels of PV and what the impacts are. Microgrids, of course, and you discussed that a little bit. The concept of virtual power plants. When you look at microgrids, there's very interesting way of really looking at the power grid or power system actually in the future as a virtual power plant rather than large generating baseload power plants and load. So that's sort of starting to happen already around us. A little bit about Envision Charlotte and then some conclusions. Now, if you look at energy security and independence, it's all about, of course, energy security in the middle, but you're looking at national security, environmental security, and economic security. So that's sort of typically seen as the big E's, around security. If we look at the especially on the EPA, and I think you mentioned some of those initiatives, and especially now that the states have to define how they want to handle the CO2 requirements. That's going to be an interesting discussion. I'm not sure if a lot of states are actually going to respond to it, but it's at least interesting to see how it sort of puts back to the states now. Infrastructure, I think, is very important. Doesn't matter if it's natural gas or electric transmission. We need the infrastructure, right? So for a long time in this country, very little investments went into infrastructure. It's very painful to install and build new infrastructure. So it is really a major problem. And as we go and move from coal to natural gas, which is sort of a trend, as you know, we're going to see a bigger impact on infrastructure, especially on the pipeline side. If we look at waste streams, yes, and the example you showed where you need to look at really a closed loop scenario where waste is used again in the energy production and so on, is very crucial. I mean, we've got a lot of coal ash, we'll still have a lot of coal ash in the future. So what do we do with all this stuff? And there are some good ways and efforts which we can actually use it. Water consumption, the nexus water and energy, it's continuously being a major issue. For every kilowatt hour we consume, we use 2 gallons of fresh water. It's really an interesting statistic. If we're really talking about independence, especially on a national security fashion, and especially if you look at what we are currently doing with a number of the military bases, the only way to be really totally independent is have one way or the other have a renewable fuel. That's source your productivity. Now, it is not realistic to accept we're going to have all renewable fuels in a very short period of time, but that is a fact. If you want to be independent, you need to have a renewable fuel. If we look at the utility business model, you also looked at that a little bit. It is changing, and I mean the larger utilities understand that there are some major changes to the industry happening, and everybody is looking at what is a good model for the future utility. Another little interesting thing, since you mentioned Apple, if you look at big data, you can see that 40 megawatt solar field and 10 megawatt fuel cell, it needs a lot of power. So your cell phone in your pocket actually uses more energy than your refrigerator in your house. You know, if you just start thinking about it, because you think of a cell phone as using very little data, very little energy, but it is backed up with a system which consumes very, very large amounts of energy. And it's currently responsible for about 2% of our total carbon emissions. It's probably going to increase very dramatically in the future, because there's not a lot of better ways of dealing with data. And the more we have and the more faster we want to control it, the more energy we're going to use. So energy and data it's like the water and energy nexus. It's going to be interesting how this develops in the future. And by the way, that's the reason why a lot of the data centers are actually here in North Carolina, because there's reliable power. It is relatively inexpensive, and it's available. And if it wasn't for low cost or relatively low cost reliable power, they would not be here. They would be somewhere else. Mm-hmm. If we look at energy security, you know, I mentioned the 4 E's, but it's really, I think the key of all of this is, first of all, go back and behavior change and look at efficiency improvements. So if we want to change the way we address these very large challenges on energy, you know, in an environment with a good economy, first thing we need to do is really look at efficiency in everything we do, from industry, buildings, homes, etc. It's all about efficiency. So in order to be looking at energy, it has to be affordable. We have to all be, you know, I came from Europe, where we pay 50 euro cents for a kilowatt hour. Here I pay between 5 and 10 cents a kilowatt hour. It's a big difference. So affordability is very important. Price volatility, especially with natural gas, going to be very, very difficult to bet against if we only build natural gas generation. Availability, resource, and distribution. It has to be available to you at your home. When you switch the light, the power has to be there. Reliable, 24/7, and especially now with a lot of storms, resiliency becomes more and more of an issue. How quickly can we get our power back? Because we can't afford to have power, you know, off for more than a few hours, because our system can't really operate without electricity. And then sustainability. If we really look at how can we sustain these very tough questions with more emissions, more CO2 production, more waste products, and more water and land use. I think you mentioned the photovoltaics. I don't believe we should put photovoltaics on land. It doesn't make sense. Cutting off a tree to build a solar panel doesn't make any sense to me. But those are really important concerns about energy. So coming back a little bit about photovoltaics, so what are some of the issues we have to deal with putting more photovoltaics in our grid? Right now, you know, PV, especially in North Carolina, is still a relatively small energy piece of the pie. If you look in California, it's much higher percentage, where it's probably getting to a 5% level, which at least during the daytime. If you look into places like Germany, there are times where the photovoltaic production are up to 30% of total use. Now, under those sort of conditions, you can anticipate these problems. We really have to address them heads on. And some of them are, you know, just straightforward things like the technology. How can we make them more cost effective? Right now, the cost is not in the solar panels anymore. It's in terms of the balance of system cost. How do we permit it? How do we install it? The racking is actually more of an issue than, you know, just the photovoltaics. How do we integrate DC into the grid? You know, if you look at the diagram down here, you can see the typical production, and this is in California. Actually, in North Carolina, it looks worse than this. This is a typical power production over a day. So you see all these very sharp intermittent power production, and obviously if you put this into a grid, that would not be very effective. So you have to either balance it with something else which can, ramp up when the PV drops down, and vice versa, or you have to have storage. So you have to put this in storage. So those are the issues. In terms of the advantages of using smart inverters, these are inverters which basically can not just generate the electricity into the grid from DC to AC, but it can also support the grid in terms of reactive power support, voltage control, integrating renewable energy storage, but also do volt-var optimization, look at efficiency improvements, and you can do all of those while you generate the electricity into the grid. So those are really very important to make sure that when we specify and design new power plants, that we have a very, very good process in evaluating and installing and specifying these inverters. Currently, it's a little bit like the Wild West out there. All the developers putting inverters on, which typically is lowest cost and doesn't really look after the grid as they should. And eventually we'll need to replace those in any case. The other issue is communications, control and communications. If you look at these devices, they're all on roofs, interconnected. We need to look at scenarios where you can control and communicate with all these devices as if they are all interconnected in a single power plant. So it may be a 200 or a 500 megawatt solar field distributed across a city, and you need to integrate those as if they operate in one single device. So that is the key, I believe, in right now where we are. And the DOE is addressing this in some FOAs, which we work with universities and the national labs and industry. But it's way beyond still what we need in terms to make this effective. So the control communications of these devices is very important. Dispatchability. Right now, a PV power plant can't be dispatched like you can do with a natural gas plant or even a fuel cell plant. You can't dispatch it, and we need to figure out how much storage do we need to make it dispatchable. If not, how can we control the ramps of these power outputs to be not so intermittent, etc. And the other thing which you also mentioned, the energy analytics, we are very interested to understand a little bit more in very, very good accuracy what is the resource going to look like in the next day, next hour, and maybe in the next few minutes. Because if we don't have that information, we can't balance the power system, which unfortunately it doesn't have any energy storage. So if you're talking about power going down like on these ramps, immediately, like in milliseconds, you have to provide ramping power. So you have to provide that power to actually balance the power system. Now, luckily today we still have a lot of spinning reserve on the grid, which basically indicate that you can run through some of these highly intermittent resources because there's spinning reserve. It's basically a large flywheel as your energy storage device. Now, if we start retiring a lot of these older plants, which makes sense to do, but at the same time, we're also retiring a lot of our ancillary services, like spin reserve, like voltage regulation, and so on. And if we don't have that capability built up in another way, then we have real problems here, especially with more intermittent resources going as a percentage of the total production. We spoke about the business model. What is going to happen, not just with solar, but in general, if we suddenly discuss the lift of the RPS, the Renewable Portfolio Standard, and the federal tax credits. We know a lot of these projects will not be viable if those are suddenly lifted. And unfortunately, the solar business has always been sort of a stepchild of politicians. So if it goes up, you know, the FTC, everybody builds solar. If the FTC goes down or is cancelled or whatever, it goes down. So you can't really build a sustainable business and the energy policy if you have those sort of fluctuations in your policy making. You know, a business owner wants to have a surety at least that he has a policy and he can build a power plant which can operate for the next 5 to 10 years at an economic you know, level. So if he is not sure what's going to happen with all these tax credits and, you know, feed-in tariffs and so on, then he can't make a decision, and therefore he will not, and we won't see the development which we really need in this area. So the business model and the politics, the energy policy in all the states and on federal level is really at a big disadvantage for all of these new developments on the grid. So I'm sure they know it, but I mean, that is some of the issues I have with our existing you know, legislation and so on, that there is just not a lot of direction on these issues. You know, I mentioned the regulatory challenges. If the utilities aren't regulated to really look at these new business models, first of all, they have no incentive to do it, and secondly, we'll go back again to burn coal. That's what I think, because it's just not sustainable as it is right now. So right now, solar is driven by the 30% FTC, and if that's cancelled, which is a big talk about in a year's time, we'll see some major companies getting out of business again, which happens, you know, every 5 to 10 years. There's this sort of cycle of renewables, and then all the renewable investments and new jobs. In North Carolina, we generate a lot of new jobs in this space, and it's going to be, unfortunately, it's going to disappear again. So we have to have a real, very clear-cut, long-term plan. How do we want to do renewables, and not every 2 and 3 years make a change to those. So, you know, I can talk a lot about this, but let's move on to, you know, what's a microgrid. Now, you already mentioned the sort of general definition. The Department of Energy is using a similar one, and so on. But it's really the issue of connecting both the load and the resource locally within a certain confined boundary, electrical boundary. And that's ideally done for areas like hospitals, military bases, university campuses, and so on, where you have generation. Maybe you use it just for backup power, but you can include renewables, storage, etc., and operate depending on market signals. You can operate either connected to the grid or independent from a grid. And the real advantage of microgrids is that they are self-contained. So if you have a calamity, if you have a major storm event or a weather event or whatever, or lose a large substation due to a terrorist attack, you can really operate the grid for long periods of time as well, totally independent of the grid. It does have a great advantage. It's not always the most cost-effective way of doing it. In some cases, it may be more effective, more expensive. It can also be not as efficient as it would be for generating power at large levels, because your efficiency of a smaller turbine or a smaller device is typically lower than would be the case for a large turbine. So, but it is more flexible, and it can be, you know, capacity match towards load can be done much faster, much quicker. That is definitely the trend, to look at these sort of microgrids, especially where you need higher reliability. You need to have a resilient part of your city to recover quickly from a weather event. or it may make economic sense to operate it this way. It has, especially if you use renewable resources or natural gas, but at a higher efficiency, with combined cycle generation, it can actually be also less impacts on air quality. So it does have quite a lot of positive impact if you design and operate it correctly. So what are the issues with microgrids right now? I think from a technology point of view, the individual components, what you've seen, you mentioned fuel cells, energy storage, electric vehicles, all these devices, they are there. I mean, we are operating these devices already for a pretty long time at pretty decent efficiencies and so on. So the technology is probably not the biggest problem with microgrids. Some technology improvements need to be done, especially on the energy management side, where you do have these smaller grids, and they have to be, in most cases, autonomously controlled, where they can actually operate and connect in the grid, out of the grid, depending on weather or price signals of electricity, whatever the case may be. So there should be a very robust area energy management system and be very visual on how it's operating. And typically you can't afford to have large operating staff and so on to operate that microgrid, so it should be mostly self-contained. And then very important on microgrids, which I think you mentioned as well, is demand response. So if you include demand response in your design, it is much easier to integrate all these different intermittent resources and so on. But again, it should be automated, and it should be on small levels. So even if you look at a microgrid, a load like a household refrigerator or air conditioning system in an industrial building or a commercial building or in your house even, may be worthwhile to control on a dynamic basis. So your so-called micro demand response systems are also very important. And there are some technology out there. There are some demand response systems already in operation, even on home level, home automation systems and so on. But it is definitely an area where more focus will end up coming for sure. And we need it actually if we want to operate more microgrid type of technologies. And auxiliary service, we already mentioned that. Now you operate basically a complete power system on a micro scale, so you need all the separate components, including auxiliary services, and for that reason you need energy storage to make those devices interconnect and interoperable with each other. So that is crucial. Business model is still a very, very tough sell to sell a microgrid, just because the revenue streams are not always very clearly defined. And you typically have 2 or 3 revenue streams to tap in order to do a good business model. It is possible, and they start to do that now in New York. The state of New York has a very large initiative on microgrids after especially Sandy. But still, if you want to make that business case work, you need to tap on those different revenue streams, and that's not always so easy in one location. Regulatory challenges, coming back to the utility of the future business model, it is right now, it's really very difficult for a utility to own and operate a microgrid. And it's even probably more difficult for an individual to sell to your neighbor. If I have a microgrid in my subdivision and we want to sell to our neighbors next door, it would be very difficult. We can't do it. Actually, in North Carolina, it's illegal. There are some legislation currently happening to try to make this energy transactions a bit more transparent and a bit more sort of available for trade, on a lower level. But it is not there yet. So that needs to change. So that may take time. There are some legislation right now on the floor on microgrids, at least on the federal level, but also on the state level. I think there's some discussion about it in some of the bills. So it is definitely a possibility, but it has to move faster in order to get this model to work on a larger scale. Grid resiliency, I think we mentioned that. That is actually a big driving force for microgrids. Most of the military bases have a very strong interest in microgrids just for exactly this reason. And they are driven from the energy security point of view, but also from the fact that they have to have zero net energy facilities. All of these military bases have a DoD requirement now to be net zero in terms of energy use. So those two really drive them in terms of looking at these new models. A little bit of the technical side, I don't want to go into too much detail here, but there are some interesting aspects to take care of on the electronic side, and I, this is in the slide, so I can leave it here. It's typically on the voltage side to try to control the voltage within specification, and in a smaller microgrid scenario, it's difficult to control things like flicker, which is sort of a flicking, annoying sort of impact on your eyes when you have voltage variations. Harmonics, and especially on standards. Right now, we still live with a standard called the IEEE 1547, and this standard is really doesn't allow us to really do microgrids. As soon as you want to island from the major grid, you basically have to switch off your system. So the law is, the standards actually not even allow us to do it. So a lot of utilities are sort of trying to get around it a little bit. There are some updates on the standards, trying to make it a little bit more open towards microgrids and distributed generation, but it's still a limiting factor. Switching a little bit to demand response. So if you want to do microgrids, you need to look at demand response. But demand response actually has even a larger role to play in larger communities. We will speak about the Envision Charlotte project, but I mean, if you look at demand response, it is very important to look at demand response even for large ISOs, because we need demand response in order to look at things like ramp rate, control of load, maximum peak of loads, and so on. And I mean, you've probably seen this curve, which is a well-known duck curve, which they start tracking what the typical load profiles are in California. With more and more solar penetration, you see the traditional double peak load profile is sort of starting to disappear because of solar. So your day peak, midday peak, sort of at 10 o'clock to 12 o'clock is sort of disappearing, and it is replaced by the production of power from photovoltaics. And the ISO have done several studies to look at the impact of base load versus peaking plants. And what you would see that if we at least continue with this trend of photovoltaic production, we'll see that we will have overgeneration risk. Now that is a real problem, because most of your base load is done by coal and by nuclear, a little bit by natural gas now, but in order to do base load, you need a very constant, relatively low cost power output. Therefore, nuclear makes a lot of sense to do it. Now, if you have more and more PV, and during the daytime you start producing more than your base load, your minimum operation of your base load, it's very, very difficult to recover after the end of the day. So in 2020, for instance, you start getting into a point where you have to switch off your major baseload generation, and then if you suddenly have a peak coming back at late afternoon when air conditioning load is actually at its peak, 6 p.m. to 9 p.m., you really have a problem because you need a lot of high ramps. We're talking about in the ISO system in California, 13,000 megawatts in 3 hours. There's really not a lot of generation you can pick up on that sort of speed to fulfill that ramp. So the only real solution we see here is two things: you put in more energy storage, or you try to do demand response. You can ramp up some natural gas generation, but I mean, if you come from a base load from 12,000 megawatts and you want to ramp up to 26 to 28,000 megawatts in an hour or two, you have some trouble. So that is really the reason why demand response is currently, got a lot of attention by a lot of ISOs, and it's important for smaller, microgrids, as we mentioned, but it's even more important for larger system operations. There's some interesting projects, and you may have seen these already, but it's one project is currently done in New York as part of the retirement of a nuclear power plant at in the Indian Point Energy Center, where they really work with NYSERDA to develop a plan to do demand response. So the whole idea is to try to limit those peaks, late afternoon peaks, reduce it by 120 megawatts, 125 megawatts, and they do it three ways, I think. The one is with energy efficiency. Actually, the majority of it, you can see 100 megawatts through energy efficient measures, and demand response, which really means they switch off load on a controlled environment. And then the rest, only 25 megawatts, with a combined heat and power scenario. They believe they can do it at a relatively good price, at about $1,600 per kilowatt, which is a pretty decent solution. It's about the same price or cheaper than a combined cycle generator, and it's definitely much cheaper than trying to build a new generator. Of course, it is there right now. It's already been busy for implementation since the last year or so, and it's going to be interesting to follow that case study and see how it operates. Some of the other initiatives on demand response is also happening in New York, and that's called the NYSERDA Lawrence Berkeley National Lab designed the open automatic demand response demonstration project. It's sort of a protocol where a number of buildings, and especially New York City buildings, are buying into this program. In a way, it's actually similar to what we have in Envision Charlotte, but a lot of these large buildings, they have installed these open ADR communication protocols, work with the ISO, New York State ISO, and New York ISO, and provide then a pretty seamless demand response system through those building operators. It is right now they have a few buildings in operation. I think 6 or 7 for a extended demonstration installation, and they base basically their demand response on day-ahead hourly price forecast, and use then the demand response to really control those pricing based on what sort of pricing is there. Make a decision on which buildings, how much can be controlled in terms of air conditioning load and so on. Very interesting project. I think we'll definitely see a lot more from this open ADR sort of protocols. It's open. We can use it actually in Charlotte or in Asheville, it's pretty straightforward. We don't have an ISO, of course, and I think you mentioned maybe there's a place for a regional independent system operator, and that may be the case in this case to use a ADR type of approach in this new RTO. The virtual power plant, this was actually something I did in my previous career, where we did start looking at virtual power plants, how you can go from actually single street light or utility pole solar panels with some communication and control capability, including residential rooftops, commercial rooftops, and so on, to integrate it all into one command and control center, where you basically do voltage control, you do dispatch of the resources, all integrated from one location. And the site is operation now already for 2 or 3 years, and it ran through Sandy, and the utility PSE&G used the system to determine where the outages were, because since these solar panels provide power directly to the grid, they could figure out exactly where the grid was down, and had a much faster response time based on these integrated systems. So and this is sort of the microgrid idea, but just now distributed across a very large area. In the case for New Jersey, this was over the whole of the state, so we are talking about a very large area where this power plant was deployed. And those sort of concepts, how we control these devices and how can we actually operate these devices over a large area, would be very interesting to follow. Right, so that is a little bit what I want to say about the microgrids, demand response, and those sort of thing. I think I can jump over to tell you a little bit more about Envision Charlotte. So these are basically our standard deck of slides. So the first thing, it is really a fantastic public-private partnership, really a very case study project. We got international recognition for this project already in a number of places. It's not so much, at least the first few couple of years or so, was not really so much on the technology side, but it was really trying to do energy efficiency with things like behavior changes, and also getting people more aware of what they use in terms of energy, water, waste, and air. So we have 4 pillars. One is energy, and we are probably the furthest ahead on the energy side. We had a great relationship with Duke Energy and some other partners like Itron to get that off the ground, Cisco systems and so on. And the basic idea is, let me see, yeah, we'll get back to the technology. So basically 4 pillars. Energy is sort of on its way. Water is next. We already have some interesting aspects on the waste side. And air is sort of a tough one because your air pollution is really not only generated from your local city area. It is generated from all sorts of areas depending on wind, and it may be driven from a generator which produces bad air quality up in the mountains or whatever. So it's not easy, but actually we want to address air, so we are currently looking at aspects how we want to do it. Now, the basic idea of Envision Charlotte, if you look at the Charlotte footprint, it took something like, I think, 90% of the buildings in the closed-in area of Charlotte. It's a total of 61 buildings, 21 million square feet of area, footprint size. It's a non-profit organization, Envision Charlotte, and it started actually with a Clinton Global Initiative a few years ago. And it is, as we call it, a public-private plus partnership, because it does include the city, public, it does include the property managers, the private owners, asset owners. It includes actually the utilities, especially Duke Energy and Piedmont Natural Gas. They are really very active with this group. It also includes the university because, you know, the skill sets and also the student involvement and so on is very crucial in this project. And we have a private sector, especially the banks, uptown Charlotte banks, taking a very, very active stance on this initiative. So the basic goal is to have the energy program. The goal is to reduce electricity use by 20% by 2020, and that is also now taken its own sort of regulatory solution through Duke Energy's Smart Energy Now program. So the Smart Energy Now program is basically the regulatory part of this project, but it was really started through Envision Charlotte. What we've done up to date is we've done an 8.4% reduction in energy use for all those buildings, and it is this was, I think, released the data about a month ago or maybe 2 months ago. So I believe we are pretty close to 10% already in terms of our original goals. Now, of course, why would the business owners be interested? Because they save money. This actually equates to a $10 million savings in electricity use. So this is really a win-win for the environment, for the city owners, but also for the businesses, because they do have you know, some economic incentives to do it. So we're also working right now on a energy roundtable. This is interesting because we are in a point now where we think we got most of the behavior changes and, you know, just the awareness of the energy use and so on. We got that sort of to the point now where we don't think we can improve it much more. The important part now is to have this, first of all, sustained over a long period of time, that people don't go to their old habits again, but also to train business, especially the building owners and operators, how to look after their system and trying to get, you know, continuously this benefit. So we call it the energy roundtables. It's basically our faculty, some students, the property owners, especially their engineers, and the manager to really do internally, building by building, an audit, and do that audit based on, you know, what's the best bang for the buck in terms of technology upgrades. So this is also, you know, as part of Envision Charlotte. So there's no vendor involvement. A lot of the business owners are actually always you know, it's difficult for them to make a decision what technology works, and, you know, why should they be giving this specific technology to move forward. So it's really that unbiased analysis of their building, and also looking at the technologies, what will help to improve that situation. So that is really a very active program, and we hope to see more of those. We also, as I mentioned, have a water program. Equipment's being installed. We have a sort of a baseline set, and we're starting to implement it. So in this case, we're trying to do a similar aspects as we did with energy, where we have, first of all, a baseline. We have some measurements, smart meters, basically, both water and electricity now, to measure the usage, and then, you know, on the cloud, make it available back to the buildings, and at least show them what they use, and, you know, how can they you know, save and consume less. In this case, as I mentioned, we have several partners. On the water side, it's mostly Itron and Verizon. The city of Charlotte basically do their own water utility as well. So in this case, it's handy because they are also already a partner in the Envision effort. Another partner is CH2M as well. So this is what we did, both for the energy and for the water. There's basically installations which went up onto lamp poles, which basically collect data from the meters, both in the buildings, sort of an extra meter installed. These are then sent to cloud storage and computing and analysis, and the results are then submitted back to the buildings in a sort of a ID-proof format. So the business owner can actually look at it, and he can compare his own results with his neighbor, but he doesn't really have the information of the building owner next door. So it sort of gives a little bit of a comparative nature, but also a competitive nature between these different buildings. On the waste side, interesting enough, most of these waste streams coming out of the city really is in terms of dumpsters, and the dumpsters have, in most cases, they don't control really, or they don't know how much are the dumpsters full, are they half, or whatever. So the idea here is we installed sensors, relatively low-cost sensors, by a company called Inevo, into the waste dumpsters at these same buildings. Install the equipment, and now on the same basis, it's sort of aggregated data. It is sent to the people who collect the dumpsters, and they know exactly at any one time how much, is the dumpster half, full, or whatever, and they can actually collect them based on full. So saving, of course, on the cost, but also save a lot on, air pollution and other way. Now, what we're also trying to do as part of a waste product is to, again, within behavior changes within the buildings, to try to get the employees of the buildings to really recycle more, trying to get the waste streams separated a little bit better, and some of the buildings actually signing up for a zero waste sort of program, especially some of the newer buildings which can have that easily integrated. So that's actually a very, very active program as well within the Envision, and we have high hopes for this pillar as well. The last one is, as I mentioned, air. Now, on air quality, we have a few sort of initiatives. We don't really have a rolled out program yet. So the waste, the air pillar is going to be focusing on things like the rental of the scooters and bicycles, but also electric vehicles, electric vehicle chargers, and trying to measure, normalized what you expect the impact's going to be. So it's going to be a more difficult sort of validation process on the air side than we will have with the others. But I think it's a good way to get started. So that is basically our scenario. We had the opportunity of visiting Barcelona recently and present the scenario, and actually were a finalist in the World Cities conference. So basically, everybody in in a lot of places in the world suddenly look at Charlotte and try to see if they can do similar things in their city, which is of course a great thing to do. So we've just returned from a trip up to DC as well, with a Smart City Alliance being signed by European cities and US cities, and so we'll see a lot of this sort of smart city activity to move forward as we move along. Well, that's it, Grant. I don't know if we have time for some questions.
Oh yeah, Johan, this is so incredibly valuable to be able to uh, get with you today and get the picture on your knowledge of microgrids and then the overall Envision Charlotte smart city, not just concept, but all of these examples of going ahead, again, going ahead and taking action. Um, so let's see, I'm going to, I think, I just want to switch back. I wanted to show you real quick before you got to go. I know. Oh, here we go. Okay, I'm going to come back as presenter, and I just wanted to show you on water. And we both, I had connected with the microgrids at Berkeley Labs folks on microgrid issues, or at least I'm tracking what they're doing in terms of energy informatics that may be useful here in Asheville and Charlotte. Their product called DER Cam, just good for it's good for evaluating the energy projects. Um, so real fast on just on the matter of water. Uh, going. Um, oh, and while I'm doing this, oh, here it is. Great. So, um, Lawrence Livermore, or now it's called it's Lawrence Berkeley National Laboratory. One of their scientists creates these really fascinating and useful infographics, and it kind of this one is in my PowerPoint that I shared with you, and I can make this individual slide available to you to pick it out. It kind of sells why be efficient, and just on the matter of water, this infographic shows all the surface fresh water that goes into big centralized power plants. Uh, uh, the thermoelectric cooling is 196 billion gallons of water a day, which is difficult for me to do the math on. You could do the math on these issues better than I could. And then over here, the other red circle is dissipated energy. The transmitted energy, I wanted to bring up real quick. The value proposition I see in you reference New York's new policies. I call it the New York Rev program. It's used. There's that acronym NYSDERA, I believe, but I call it the New York Rev program
Right.
is
Yeah.
another way that they frame it. And it's kind of taking where California has gone, but of course, using lessons learned and adapting and going into the nooks and crannies of efficiency better, based on what they did when they maybe looked at California's climate change fighting techniques and what's happening in other parts of the world. But in any case, that dissipated energy of 60 quads a year, and a quad is a giant. Just one quad is a huge energy
Yeah, I
Um,
mean, 60 or 70% of all energy,
right,
goes into waste.
right,
So take the kilojoules from in coal or natural gas, about 60% of it, well, natural gas is a little bit better, luckily, but 60% of it goes into heat.
right.
So that's exactly what you show there. So absolutely.
And I know we're not there yet, and I think I remember I mentioned you talked about DOE funding opportunities, and I just tried to help in any way I could with Dr. Michael Walters' efforts in photo, um, uh, uh, basically not solar PV. Well, he has a solar PV solution, but new approaches to hydrogen production.
Yeah.
And it's not completely there yet, but I showed one example of where fuel cell energy is working with biogas to answer that problem of getting hydrogen into vehicles. But you mentioned renewable fuels, and I just wanted to tie up everything that for folks who get this webinar, that I say to folks, whether it's the International Energy Agency or the Department of Energy or the EPA, there is no renewables only model for running the civilization, running the show. And you just gave us a great, it's going to be a lot of new information for folks. There is no simple angle to it. It's many angles working to get a better business model that's sustainable. But it's worth going there into these complexities, because in these complexities in the system is the new value creation. And in any case, so I'm not saying there is no renewables only solution, because I don't want renewables to be in the picture. But we've just described, and you really helped describe how these solutions demand new approaches going way beyond what we thought of as an energy efficiency demand response. These programs, we talk about microgrids, they surround and amplify what renewables can do. Hydrogen acts as one of the renewable fuels when we do get better um, renewable driven solutions to hydrogen production. I recognize right away that fuel cells do use natural gas from a natural gas system as is today, for the most part. But each of these small innovations add up to a hopeful picture of humans once again saying, we've created some inefficiencies and we've created some big environmental problems, but by digging in and using our ingenuity and frankly, I hope we do get more into evidence-based policy and drop politics, and say more people just say, well, it's time, whether you're on efficiency principles to compete with other nations and other parts of the U.S. that are advancing. But we don't want it to be the classic competitive environment, because there's too much value in cooperation. And finally, I just want to say that I hope that we here in Asheville, if we're not collaborating with you there at UNC Charlotte enough, and there's enough people asking about Envision Charlotte up here in Asheville, I hope that either I'll be able to recruit some decision makers from Asheville to come visit you all and have an event in the Charlotte area, maybe at UNC Charlotte, or we can do something up here where we have um, expand this, and I give a lot more lead time and add a lot more marketing work to doing another event like this, to get more people to the table and learn about this energy innovation world.
Yeah, no, absolutely. You're most welcome. And if we can make a tour and talk about these things. So no problem, absolutely.
Well, Johan, you've spent a lot of time with us, and I've recorded all of this. I'm going to share the videos as soon as I get them done, and I will be in touch. And I really appreciate your time today, Johan.
Okay, and I will send you the presentation as well.
That is excellent because I've just promised Kathy Ball, the City of Asheville urban design executive, that I would share my PowerPoint, and I know she'll relish yours.
Okay, no problem.
Thank you so much, sir. Have a good day.
Talk to you later. Bye-bye.
Yeah.